Okay, so hi everyone. We are going to continue lesson 3.2 and finish lesson 3.3 in this video. Lesson 3.2 is about multiplying polynomials, and lesson 3.3 is about dividing polynomials. So let's begin by finishing lesson 3.2. Now, the topic we're going to focus on today is the binomial expansion. So this is part of 3.2. It's the second part of 3.2. And the binomial expansion means how do we expand something like x plus y to the power 3. Notice that this is a polynomial multiplication, x plus y times x plus y times x plus y, right? And we can do it this way. We can just first multiply these two. So we get x plus y times x squared plus xy plus another xy plus y squared. And I can put those two xy's together in the middle to make 2xy. So that's, multiplying those first two xy's, and now I have to multiply by this third xy here. And when I do that, I would get just a bunch of terms, x cubed plus 2x squared y plus xy squared plus yx squared plus 2xy squared plus y cubed. And when you clean this up and put all the things that are like each other together, so we're going to put this one, x squared y, and this one, which is yx squared, but that's the same as x squared y. We're going to put those two together to make 3x squared y, and then we can put this one, xy squared, together with that one to make 3xy squared, and then y cubed. Okay, so that's our final answer, but it's kind of a pain to get there because of all those terms that we have to keep track of. And you can imagine that if you had to do x plus y to the 10th, this would be quite a pain to do in this way. So we have a shorter and faster way to do this, and that goes like this. Let's just begin again with that same example, x plus y, the quantity cubed. And what we're going to do is we're going to make a little table, and once you get good at these, you do not need to make the table, but initially it helps to make the table. So the table is going to have 3 rows, and what I'm going to do is take the first term in the binomial, that's x, and I'm going to start writing the powers of x, starting with this highest power, so x cubed, x squared, x to the 1, x to the 0. Then I'm going to take the second term in the binomial, which is y in this case, and I'm going to write the powers of y, except I'm going to go the other way, y to the 0, y to the 1, y squared, y cubed. So descending powers for one term and then ascending powers for the other term. And then I'm going to put in the third row something, this is going to be the coefficients, right? And the coefficients are the numbers that are going to multiply our final answer. So here the 3 and the 3, those are the coefficients, right? And my coefficients are going to be 1, 3, 3, 1. And I will explain in a second where those are coming from. But the way we get our final answer is just going to be, once we set up the table, we're going to multiply these 3 terms. So we're going to multiply downwards, and then multiply those and these. Okay, so my final answer will be x cubed times y to the 0 times 1. Y to the 0 is just 1, so this is x cubed, plus x squared times y times 3, x squared times y times 3, plus x times y squared times 3, plus x to the 0 is 1, so this is just y cubed. Now if I just rearrange this, then you can see that it's exactly the same answer that we got back here. Okay, same answer is here now. And you'll notice kind of a pattern to this answer. you know, the x power starts at 3 and then goes down 3, 2, 1, and then 0 in the last term. This should be a y cubed right here, not a y3. So, and then you'll see that the y power starts with y to the 0. You can think of a y to the 0 being there, which is just 1. And then y to the 1, y squared. Here are the powers of y. Y to the 1, y squared, and then y cubed, right? So this is the general way in which we're going to expand a binomial, and we're going to do a couple more, a little bit more tricky examples to help you understand this. But before I do the examples, I still haven't told you where I got these numbers from. Well, I get them from what's called the Pascal's triangle. And Pascal's triangle is a very interesting mathematical construction. It's named here after Blaise Pascal, who was a very famous French mathematician. But Pascal's triangle, people say, was invented much earlier by the Chinese or the Indians or other cultures as well. But Blaise Pascal, a French mathematician, made this more famous, I would say, in the 17th century. And the Pascal's triangle is built like this. We start with a 1 on top. Actually, I like to think of it as starting with 3 1s like that, and then, you know, 1s down on the sides. So we're going to just keep the 1s all along the sides, and then in the middle of the triangle, so here's kind of a triangle shape, that's why it's called a triangle. In the middle of the triangle, we're going to build up our numbers by adding the two numbers that are just, you know, to the top, right and left. So 1 plus 1 makes 2, so that's going to go here. And then, so that's the third row of Pascal's triangle. Now the fourth row of Pascal's triangle always starts and ends with 1, but then to put the numbers in the row, we would go 2 plus 1, and we would get 3, and then again 2 plus 1, and we would get 3. So the fourth row will be 1, 3, 3, 1, and the fourth row is what I used here for these coefficients, 1, 3, 3, 1. And I knew I had to use the fourth row because you always use the row which is 1 higher than the power you're expanding to. So here I was expanding to the third power, so I'm going to use the fourth row of Pascal's triangle. So we can continue to build this triangle up as far as we want. We're just adding the numbers that are above to get the next row. So 1 and 1 on the two ends, and then 5, 10, 10, 5, 1. Okay, so that's Pascal's triangle in a nutshell. And Pascal's triangle makes these binomial problems quite easy, the binomial expansion. So let's try another one. Let's try x plus 4 to the power 4. So you don't even have to make the table. You can just write the 3 rows, x to the 4th, x cubed, x squared, x to the 1, and then x to the 0, which is 1. And then that's because that's this term, the powers of that term. Now the second row is going to have the powers of this term, and I would like you to take the sign with the term. So here we're going to have the powers of 4, of positive 4. Except I'll start with 4 to the 0, which is 1, then 4 to the 1, 4 squared, 4 cubed, and I'll end with 4 to the 4, okay? And then in my last row, I'll have my Pascal's coefficients. Okay, and so since I'm raising something to the 4th power, I'm going to be in the 5th row of Pascal's triangle, and here's my 5th row, and I'm going to have these numbers from here in my 5th row, 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1, and if I just multiply downwards, remember you're multiplying down like that, we get x to the 4th plus 4 times 4 is 16x cubed, plus, now we have to be careful because this 4 squared can be written as 16, and we have to do that. So 16 times 6, I believe that's 96, so we would get 96x squared, And now this 4 cubed has to be rewritten as 64. So 64 times 4, I believe that's 256. So we would get 256x plus, in the last piece here, we have 1 times 4 to the 4 times 1. And 4 to the 4 is also 256. So this will be my final answer right there. Okay, things can get a little more tricky when you have a negative, so I want to make sure I do an example, a couple more examples, one with a negative. So if I have y minus 3 to the power 4, so I am in the 4th power, therefore I will be in the 5th row again, as in the last example for my Pascal's coefficients. And I can just begin by the powers of y, so take that and write its powers, and those are going to be y to the 4th, y cubed, y squared, y to the 1, y to the 0, which is 1. And then I take my second term in the binomial along with its sign, and I will do negative 3 to the 4th. I'm going to first write it like that. Oh, sorry, I should have actually started with negative 3 to the 0, right? And then negative 3 to the 1, negative 3 squared, negative 3 cubed, and negative 3 to the 4th, okay? And now I'm going to just actually just rewrite this whole table here just to show you how very clearly I'm simplifying. So negative 3 to the 0 is 1, and negative 3 to the 1 is negative 3. Negative 3 squared is positive 9. Negative 3 cubed is negative 27, and negative 3 to the 4th is positive 81, okay? So you're going to see that the signs here, when the second term in the binomial right here was negative, your signs are going to alternate in the powers of that second term, okay? So just recognize that, and then we're going to put in our Pascal's coefficients from the 5th row, so 1, 4, 6, 4, 1. And now we have to just multiply it all out to get our answer. So we'll get y to the 4th minus 12y cubed plus 54y squared minus 108y plus 81, okay? So you can get some pretty big numbers there in your final answer, and that's just fine, you know. And if you took the time to do y minus 3 times y minus 3 times y minus 3 times y minus 3, and you did that whole multiplication out, then you would get exactly this number. But I think you'll agree that this is just a much faster way to get the answer. Okay, and then the last example I want to do is this one, 4z plus 5 to the power 3. And so my first term now is 4z. So my powers will be 4z to the 3rd plus 4, not plus, just list them separately, 4z, the quantity squared. And that's what I wanted to show you in this example, is that I'm doing 4z, right? That whole first term, you're taking it to the power. So 4z cubed, 4z the quantity squared, 4z to the 1, 4z to the 0, which is 1, right? We'll simplify that in a minute. And then I have to take 5, which is here, and do its powers. So 5 to the 0, 5 to the 1, 5 squared, and 5 cubed. And we can simplify all of this. We do have, of course, to write our Pascal's coefficients, and they will be from the 4th row of the triangle. And so it'll be 1, 3, 3, 1. It's the 4th row because it's to the power 3, so it will be row 4. Pascal's triangle, row 4. And so those are coefficients, and so we now have to simplify these terms here. And so this will be 64z cubed, 16z squared, 4z, and 1. And the other one will be 5, I'm sorry, not 5, 0, 1. 5 to the 0 is 1, 5, 25, 125. And then we have 1, 3, 3, 1. and we're going to multiply down again, always multiplying down and keeping the sign whatever it happens to be. And so we will get 64 positive, 64z cubed. Everything's positive in this case because the binomial was 4z plus 5, right? So anyway, we get here 15 times 16, that would be 240z squared. And then here we have 100 times 3, so that's 300z plus 125. So that's our final answer. Two terms. And so we took that. Hello everyone. So in this second part of the video, we're going to talk about polynomial division mainly. And polynomial division is in lesson 3-3 of your textbook if you want to look up any details. We're going to do three things. The first is long division of polynomials. The second is called synthetic division. And synthetic division is a shortcut way of doing long division. And then we're going to lastly talk about something called synthetic substitution. So let's begin with long division. So long division of polynomials is very similar to long division of numbers. So I'd like to begin by reviewing how we divide numbers. So you did this back in, 6th or 5th grade. But let me remind you that if you're dividing a number 7,269 by 4, the way you do this is in your mind you think about, does 4 go into 7? Yes, it does. It goes in there one time. We call that step that I just did the divide step. Then I say 4 times 1 is 4, and I then multiply 4 times 1 and put 4 there. That's called the multiply step. Then I subtract 7 minus 4, I get 3. That's my subtract step. And then I bring down the next digit, so I bring down the 2. And that's called the bring down step. So divide, multiply, subtract, bring down, and then repeat. Now I look at 4 going into 32, and I say it goes in 8 times. That's divide, multiply, subtract, bring down. Divide, multiply, subtract, bring down. And again, divide, multiply, subtract, and there's nothing left to bring down. So I'm done, and I can write my quotient in this way. I can write my answer. The answer to a division problem is called a quotient. I can write it this way: 1,817 and 1 divided by 4. So whatever remainder is left over, I take that and I put that over the divisor. So I have up here the quotient, and the final answer will be 1817, and then the remainder 1 divided by 4, 18,117 and 1/4. And I'll also remind you that if I now take that answer, 18,117 and 1/4, and multiply that by 4, then I'll get back the number 7,269, which is inside the box there. And by the way, that is called the dividend. So we have this vocab that we're going to be using: dividend, which is this number, divisor, which is the number we're dividing by, and the quotient. And of course, we also have the remainder. And all these words are going to be used in our polynomial division, because polynomial division is going to be very similar to this. By the way, in case your 5th grade teacher didn't tell you, you can remember this by, divide, multiply, subtract, bring down. There's various mnemonics for that. Does McDonald's serve burgers? Dead monkeys smell bad. You might have another one, favorite one that you like, but it's a way to remember the process of division. And so we're going to do the same thing now. We're going to divide this polynomial, 4x squared plus 3x cubed plus 10, and we're dividing this by x minus 2. So we have a polynomial divided by another polynomial. And we are first going to identify that this is the dividend and this is the divisor. So we make our box and we put the dividend inside. Oh, before I do that, I want to do something to the dividend. The dividend right now is not in standard form, right? So my dividend is not in standard form, and I need to make it into standard form when I put it into the box. So we're going to do that. So it's going to be 3x cubed plus 4x squared. And now notice there's no x term. You want to put 0x in that case. So any powers that are not represented in the original polynomial, you're going to put them in with 0 coefficients, so that once you write this into the box, every power has been represented. We have an x cubed and an x squared, an x, and then the number. You want it to be like that. And then we're going to go ahead and write the divisor outside here. So this is x minus 2. And then we begin the process of long division. So the first step is divide. So what I'm going to divide is this 3x cubed by this x. So 3x cubed divided by x is 3x squared. And if you're confused about y, just think about what do you need to multiply x by to get 3x cubed. And you'll realize that what we need is 3x squared. And that's how we say that 3x cubed divided by x is 3x squared. So that's the divide step. Then we multiply. So we get 3x cubed, which is what we want. But we're also going to multiply this. We're going to say now minus 6x squared. So we've done the multiply step. Now we're going to do the subtract step. So when you subtract, you want to subtract this entire thing. You want to make sure you put parentheses there. And then go ahead and subtract. So the first terms will go away, and then we get 4x squared minus 6x squared. So that makes 10x squared. So we did subtract, and now we're going to bring down. And notice that what I'm going to bring down is that 0 coefficient that I set up before, and that's fine. Now I'm going to do divide again because I'm back to the beginning. Divide, so I get plus 10x. Multiply, so I get now 10x squared minus 20x. Subtract, that will give me 20x, and then bring down. And so I'm now back to divide, plus 20, multiply 20x minus 40, subtract, and there's nothing left to bring down, so I'm done. So this is my remainder. Up at the top is the quotient. So here's the quotient. And the way I write my final answer will be the quotient plus the remainder over the divisor, just like we do in a number problem. So that's the process of long division with polynomials, and that's the first thing you need to be comfortable with in this lesson. Now, the second thing we're going to learn to do is a shortcut way to do what we just did. So I'm going to take the same exact problem, 4x cubed plus 3x, I'm sorry, it was 4x squared plus 3x cubed plus 10, right, divided by x minus 2. And we're going to use the process of synthetic division to do what we just did with long division. We're going to get the same answer because synthetic division is just a shorthand way of dividing a polynomial by a linear binomial. Notice this is a linear binomial. So when we have the divisor being a linear binomial, we can shorten the process of long division. And the way we do it is in this way. We begin by taking the polynomial, putting it into standard form, right? So standard form, and zero coefficients, we do the same thing we did in the first step of long division. So we're going to write it as 3x cubed plus 4x squared plus 0x plus 10. Don't forget to include this term, add in that term, okay? Now, the next thing we want to do is write these coefficients in this way. We're going to take the coefficients, those are just the numbers, right, and write them like this: 3, 4, 0, and 10, okay? Now I'm going to set up a box like this. It's kind of like a backward facing L, and in that L we need to put a number, and that number is going to come from the divisor, okay? I'm going to take my divisor, which is x minus 2, set it equal to 0, and solve that little equation. So I get x is equal to 2. This number that I get when I solve the equation is the number that will go in here. Then I come on and I draw a line here, and I'm going to bring this first coefficient down under the line. And now I'm ready to begin the process of synthetic division. And the way it works is we multiply the 2 by the 3, and we get 6. And now we're going to add 6 and 4 to get 10. And then I'm going to multiply again, 2 times 10 to get 20. And I will add now to get 20 again, and then I multiply again, and I get 40, and I add to get 50. And that's the sort of the procedure. And now how do we interpret the answer? So to get the answer after a synthetic division, we're going to realize a couple of things. We're going to realize that we started out with a polynomial, which we wrote as 3x cubed plus 4x squared plus 0x plus 10, right? So we could say this was our dividend polynomial, and then we divided it by our divisor, which was a linear binomial. So here's our divisor, which was a linear binomial. Linear because it has just a power of x to the 1, and binomial because and we want to come out with a quotient, right? There will be a quotient, and then there will be a remainder which we're going to put over the divisor. That's going to be the way our answer will come out. Now, the quotient will be a polynomial, and it will be 1 degree less than the dividend. And the reason is we divided by this linear binomial. So we're dividing, there's an x term here in the linear binomial. So it kind of makes sense that when we do our division, we're going to reduce the degree of that dividend by 1. So our quotient is going to be 1 degree less than the dividend. And so now, once we realize that, we can go here and take these first 3 numbers. Those are going to be the coefficients of our quotient. This number at the end is always going to be the remainder. This is going to be the remainder. So this goes in here. We can just plop the remainder on to this piece of our answer, because that's the place for the remainder. And these first 3 numbers will line up with our coefficients for the quotient. We know the quotient is a second degree polynomial because the dividend here, this guy, is a 3rd degree. So 1 degree less than that is 2nd degree. So our quotient has to be x squared and x and a number, x to the 0. This is x to the 0. So the quotient will be, in our case, 3x squared plus 10x plus 20, okay? And if you compare to the answer we got a little bit earlier in long division, it was exactly the same thing. So the process of synthetic division, of course, this first time that I did it, it probably didn't seem much shorter, but let's do one more example to convince you that synthetic division is really a quick process, and it's easier in many ways than long division. Let's do this example now here, which is example 2, for synthetic division, 4x squared minus 12x plus 9, and I'm going to use a linear binomial divisor. Of course, that's what I have to do, but I used a fraction here, so that you can imagine that in the long division that would make the problem even a little harder, but synthetic division makes it very easy. So I go 4, negative 12, 9. I'm setting up my synthetic division. I checked that it was in standard form, and there were no powers of x missing, so I don't need to add any zero coefficients. Then I take that divisor, set it equal to 0, solve that. X is equal to negative 1/2. I put the negative 1/2 here. Then I draw my line, bring the first coefficient down, and begin the process of multiplying and adding. So I get negative 2. Add those to get negative 14, then I get positive 7, add those to get 16. I know this is my remainder, and I started with a second degree polynomial, so my answer will be a first degree polynomial, which means it'll have an x term in it, x to the 1, and an x to the 0, in other words, a number, okay? So my answer will end up being 4x minus 14 plus 16 divided by the divisor, which was x plus 1/2. So here's my answer, and that was pretty fast to generate. So the last piece of our lesson is called synthetic substitution, and this is how it works. Synthetic substitution is used not to divide polynomials, but to evaluate polynomials. So let's first be clear what we mean by evaluating a polynomial. So a polynomial can be written like a function. P of x is equal to x cubed minus 4x squared plus 3x minus 5. So think of it as a function equation. And when I say let's evaluate this polynomial, evaluate at x is equal to 1, then I'm saying put in 1 for x, and we write that as p of 1 is 1 cubed minus 4 times 1 squared plus 3 times 1 minus 5, and we get, 1 minus 4 plus 3 minus 5, which is negative 5. So this evaluation process can also be done through the synthetic division process. So what we do is, if we're trying to evaluate this polynomial at x is equal to 1, we can take the polynomial, write it out as a synthetic division, 1 minus 4, 3, negative 5, and use this number 1 that we are trying to evaluate it at as our number in that backwards L box. That's the number we're going to use in the process, and we just do the synthetic division. And so I'm just doing that right now, and we get here the synthetic division, and here is the remainder, right? And you will notice that the remainder is exactly equal to p of 1, and that will always be the case. Whatever this number is, the remainder is going to be equal to p of that number. In other words, the polynomial evaluated at 1 is equal to negative 5, as we already knew from what we did up here. So what we did in the first, I'll call this, case 1, and this one case 2. In case 1, we literally plugged our number 1 into the equation and we got out an answer. That's called direct substitution. We evaluated the polynomial at a particular x value by direct substitution. This should be substitution. And in the second case here, what we did, if we were to do the synthetic division and get the answer from here, this is called synthetic substitution. Now you'll notice we did exactly the same thing as what we did in synthetic division, except in synthetic division we wanted to write the quotient polynomial and then the remainder divided by the divisor, right? We wanted to write the answer in that format. The goal was different. In synthetic substitution, the goal is simply to evaluate the polynomial at a given value. And the reason it works is something called the remainder theorem. And if you're interested in why the remainder theorem works, take a look at your book. They explain it somewhat, and I would be happy to explain it further. But the remainder theorem tells us that when we do a synthetic division process, then this remainder that we're left with is also equal to the polynomial evaluated at this number right here. So let's finish with one more example of synthetic substitution, which is this one. It says use synthetic substitution to evaluate this polynomial p of x is equal to 4x to the fourth plus 2x cubed plus 3x plus 5 for x is equal to negative 1/2. So first of all, we set up our synthetic division, noticing that we're missing an x squared term, so we have to put in a 0 for that. And so that's my coefficients, and in the box I put in the number at which I'm trying to evaluate the polynomial. Then I set up my synthetic division and I get the answer, which will be, in this case, equal to 5 minus 3/2. That would be 7/2, right? This is my answer in terms of the remainder. It's the remainder, as well as it is p of negative 1/2, right? This 7/2 is equal to p of negative 1/2. It's the polynomial evaluated at negative 1/2. And we've got this answer by doing synthetic substitution. Let me just double check it by doing direct substitution. So p of negative 1/2 would be 4 times negative 1/2 to the fourth plus 2 times negative 1/2 cubed plus 3 times negative 1/2 plus 5. And if you do that right, let's check it out. 1 over 16 plus 2 times negative 1 over 8 minus 3/2 plus 5. So I think I get 1/4 minus 1/4 minus 3/2 plus 5, and that is equal to 7/2. So we confirmed it, right? But here's the thing. Very often the synthetic substitution, if you're doing it for a fraction, if this number you're evaluating at is a fraction or it's a big number, the synthetic substitution is actually going to be easier than direct substitution, right? So we can always do direct substitution, but sometimes synthetic substitution is just going to be faster and easier. Of course, a lot of these techniques were developed before we had Desmos and calculators at our fingertips. So to some extent, these procedures are not as useful today as they used to be in the past, but it's still interesting math to learn them. And I hope that you understood everything, and make sure you do the homework, and I'll see you in class.